On October 3rd, 2025, an object from another star system passed closer to Mars than any previously observed interstellar visitor had ever come to any planet in our solar system. The distance at closest approach was 0.018 astronomical units. In raw terms, that is approximately 1.68 million miles, or 2.7 million kilometers, roughly the equivalent of less than 7 times the average distance from the Earth to the Moon. And we had eyes on it, not one pair of eyes, not two. 5 separate NASA missions, 2 orbiters circling Mars, a rover sitting in the dust on the Martian surface, 2 interplanetary spacecraft en route to other destinations, and a fleet of solar observing instruments spread across the inner solar system, all watching simultaneously as humanity's most exotic visitor in recorded history made its closest approach to another planet and then passed by forever. What those missions saw and what they measured, and what the scientific community has extracted from that data in the months since, is the most detailed and most multi-dimensional portrait ever assembled of an interstellar object in any solar system. And the story of how NASA pulled off one of the most complex multi-mission observation campaigns in the history of space exploration against a compressed 3-month timeline that nobody had planned for is as extraordinary as the science itself. Start with the geometry. 3i Atlas was discovered on July the 1st, 2025 by the Atlas Survey Telescope in Chile. From that moment, scientists had approximately 3 months before the comet made its closest approach to Mars. 3 months to coordinate observations across multiple spacecraft in different orbits around different bodies, file observation requests through mission operations teams, obtain approvals, write commanding sequences, verify instrument configurations, and execute everything without a single significant failure. That kind of coordination, conducted at emergency pace, represents exactly the kind of institutional agility that NASA rarely gets credit for from the public. The Mars Reconnaissance Orbiter was the mission that produced the closest and sharpest optical images of 3i Atlas of the entire global observing campaign. MRO is primarily a Mars surface mapping spacecraft. Its flagship camera, the high-resolution imaging science experiment known as HiRISE, was designed and built to photograph geological features on the Martian surface in extraordinary detail, resolving objects as small as 25 centimeters from a cruising altitude of roughly 300 kilometers above Mars. HiRISE photographs rocks, it photographs dust devils, it photographs ancient riverbeds and impact craters. It was not designed to be a comet observatory, but the physics of precision pointing that allows it to photograph a boulder on a Martian hillside from orbit also allows it, when the spacecraft rotates appropriately, to point upward at a celestial object and photograph that instead. On October 2nd, 2025, the HiRISE camera aboard MRO captured 3i Atlas from a distance of 30 million kilometers, or 19 million miles. These images were among the closest views that any NASA spacecraft or Earth-based telescope obtained of 3i Atlas during its entire journey through the solar system. The HiRISE image shows the comet's fuzzy coma, the cloud of dust and gas surrounding its nucleus, as a distinctly resolved structure rather than just a point of light. Shane Byrne, the principal investigator for HiRISE at the University of Arizona, described the occasion with understated scientific enthusiasm. He said that observations of interstellar objects are still rare enough that scientists learn something new on every occasion, and that turning a surface mapping camera toward a passing interstellar comet represented exactly that kind of exceptional opportunity. The image MRO captured on October 2nd showed something that became scientifically significant almost immediately upon analysis. The brightness profile of the coma, the way the light faded from the central nucleus, outward through the surrounding cloud of gas and vapor allowed scientists to refine estimates of the nucleus's size. The coma itself, the outer envelope of gas extending away from the solid nucleus under the pressure of sunlight and the solar wind, had been estimated from earlier Earth-based observations to span roughly 700,000 kilometers in diameter at its greatest extent, larger than the entire diameter of the Sun. The MRO images, taken at the closest distance any spacecraft achieved during the mission, gave scientists a higher resolution measurement to work with in constraining the physical properties of the central body producing all of that gas. Maven, the Mars Atmosphere and Volatile Evolution Orbiter, contributed something that no other instrument in the entire global observation campaign could provide. Maven carries the Imaging Ultraviolet Spectrograph, a camera that operates in ultraviolet wavelengths invisible to human eyes and to most conventional optical telescopes. Ultraviolet light is particularly useful for studying comets because it reveals the presence of hydrogen, which is produced when water molecules in the comet's coma are broken apart by solar ultraviolet radiation into their component atoms. Maven captured images of 3i Atlas over the course of 10 days from September 27th through October 7th in multiple ultraviolet wavelengths. The images provided the most detailed breakdown of the comet's chemical composition of any observation made during its solar system passage. The ultraviolet images from Maven showed something that required careful interpretation. The image revealed 3 distinct sources of hydrogen simultaneously. On the far left of the frame appeared a dim, compact spot corresponding to the hydrogen released by 3I Atlas as its water ice warmed and broke down under solar radiation. On the right side of the frame appeared the much brighter hydrogen emission from Mars itself, the hydrogen atoms present in the thin Martian upper atmosphere. And in between appeared a faint, diffuse emission from the interplanetary medium, the hydrogen threading through the inner solar system from the solar wind and from other sources. Maven's spectrograph separated these 3 components from each other using their different velocities, because atoms moving at different speeds toward or away from the spacecraft produce slightly shifted spectral signatures that can be distinguished from each other through a technique called Doppler analysis. The fact that Maven could detect 3I and Atlas in ultraviolet as a distinct, separate source of hydrogen emission from everything else in the image confirmed directly that the comet was releasing water, not assumed to be releasing water based on brightness measurements, not inferred from ground-based spectroscopy, directly detected, spectrally resolved from surrounding sources, measured in the actual hydrogen atoms produced by photodissociation of water molecules at the comet's surface. Maven detected different types of hydrogen, including hydrogen, released as 3I Atlas warmed up and began releasing water vapor. These findings could offer hints about where 3I Atlas originally came from. The hydrogen to deuterium ratio that Maven's ultraviolet spectrograph attempted to constrain in its October observations, though not fully resolved at the precision that Webb's later infrared observations would achieve, provided the first attempt at characterizing 3I Atlas's isotopic composition from the unique vantage point of Martian orbit. Then there was the image that, in a different way from any of the others, captured something that felt genuinely historic. On October 4th, 2025, NASA's Perseverance rover paused its work inside Jezero crater on the surface of Mars, pointed its Mastcam-Z camera at the sky, and took a picture of 3I Atlas. The comet appeared as a faint smudge against a field of background stars whose own light had smeared into streaks during the long exposure time required to detect something so dim. The image was technically challenging to produce and scientifically modest in what it revealed compared to the orbiter observations. But what it meant symbolically and historically was almost impossible to overstate. Perseverance was exploring the rim of Jezero crater when it spotted the comet. The exposure had to be exceptionally long to detect such a faint object. Unlike telescopes that track objects as they move, Mastcam-Z is fixed in place during long exposures, producing star trails as streaks in the sky, with the comet barely perceptible. An interstellar object, an object from another star system, seen from the surface of another planet by a robot built on Earth. The comet had crossed the interstellar medium, entering the solar system from a direction toward the center of the Milky Way. It had swung around the sun and was now retreating outward. And a camera, sitting inside a crater on Mars, a crater that was itself an ancient lake billions of years ago, had looked up and photographed it. No previous generation of humans had had the technological capability to achieve any element of that chain of events. The entire situation would have been science fiction to any scientist alive before the space age. But the observation fleet did not end with Mars. Across the inner solar system, a coordinated armada of missions turned their instruments toward 3I Atlas during the September and October 2025 window. NASA's Punch mission, the polarimeter, to unify the corona and heliosphere, which launched in March 2025 specifically to study the solar corona and the solar wind, observed 3I Atlas from September 20th through October 3rd, when the comet was between 231 million and 235 million miles from Earth. The combined punch images showed the comet's tail as a short elongation extending away from the sun, the classic sign of solar radiation pressure and the solar wind pushing cometary material in the anti-sunward direction. The tail's orientation and length in the punch images provided constraints on the dust and gas ejection rates from the nucleus. NASA's Stereo A spacecraft, which monitors the sun and the inner heliosphere from a position ahead of Earth in its orbit, also detected 3I Atlas as it approached perihelion. The ESA and NASA joint SOHO mission, the Solar and Heliospheric Observatory that has been watching the sun continuously since 1995, captured a faint image of the comet between October 15th and 16th, 2025, as it transited through SOHO's field of view near the sun. The Parker Solar Probe, NASA's mission that periodically dips closer to the sun than any previous spacecraft, offered yet another unique vantage point during 3I Atlas's perihelion passage. Further out in the solar system, 2 interplanetary spacecraft, en route to their primary scientific targets, took advantage of their positions to observe 3I Atlas from angles unavailable to any Earth-based or Mars-based observatory. NASA's Lucy spacecraft, which is traveling through the outer solar system to study Jupiter's Trojan asteroid populations, observed 3I Atlas from a distance of approximately 240 million miles. The Lucy observation provided a unique perspective on the comet from a vantage point roughly perpendicular to the comet's orbital plane, which allows scientists to study the three-dimensional structure of the coma and tail in ways that observations from a single viewing angle cannot. NASA's Psyche spacecraft, which is en route to the metal-rich asteroid 16 Psyche in the main belt, also contributed observations from its own position in the solar system during the same period. ESA's JUICE spacecraft, the Jupiter Icy Moons explorer currently traveling toward the Jovian system on a long interplanetary trajectory, turned its Janus navigation camera toward 3I Atlas on November 6, 2025, capturing one of the most visually striking images produced by any spacecraft during the entire campaign. The JUICE observation was made from a particularly favorable geometry, as the spacecraft's position in the solar system placed it at an angle relative to 3I Atlas that was complementary to the views obtained from Mars and from Earth. The resulting image showed the comet glowing against a background of stars, with its coma extending asymmetrically in the anti-sunward direction, the classic signature of solar radiation pressure pushing cometary material away from the sun. The image was not just beautiful, it was scientifically useful, providing another data point on the coma's structure and the comet's activity level weeks after perihelion, during a phase of its retreat that ground-based observatories were just beginning to recover visibility of. The data from that JUICE observation was downlinked to Earth in 2 marathon 11-hour sessions in February 2026 through ESA's Deep Space Antenna Network, a logistical effort that reflected how seriously the scientific community was treating every piece of data this object could yield from every possible vantage point. The MRO images revealed something else beyond just the coma structure. When scientists processed the October 2nd HiRISE images and a subsequent follow-up image taken on November 20th, they noticed an unusual pattern in the brightness distribution around the nucleus. The images showed what analysts described as an X pattern in the coma structure, a cross-shaped distribution of brightness that is sometimes associated with jets of material being ejected from specific active regions on the comet's rotating nucleus. Jets of gas and dust from active surface regions, warmed preferentially as the nucleus rotates and different areas face the sun, create localized outgassing events that appear as elongated brightness, enhancements extending from the coma in specific directions. The X pattern that appeared in both October and November HiRISE images suggested that 3I Atlas had at least 2 distinct active regions on its nucleus, separated in orientation in a way that created intersecting jet directions visible in the images. That structural information is directly relevant to constraining the nucleus's rotation rate, its shape, and the distribution of volatile ice across its surface. The Maven water data also produced a genuinely surprising number. Scientists had expected that an object forming in conditions colder and more ancient than our solar system might have a different ratio of water production to nucleus size than comets from our own solar system. The actual water production rate measured from Maven's hydrogen emission data, combined with nucleus size estimates from the MRO images, suggested that 3I Atlas was releasing water at a rate consistent with a highly volatile surface composition, more active than most solar system comets of comparable size at the same heliocentric distance. That level of activity at a distance of roughly 1.4 to 2 astronomical units from the Sun was consistent with the detection of methane and carbon dioxide in earlier Earth-based and Webb observations, both of which are more volatile than water, and would drive even greater activity at larger distances from the Sun. The comet, in other words, had been even more spectacularly active earlier in its approach than the October Mars proximity observations captured. The 2-month gap in observations that occurred while 3I Atlas was too close to the Sun to observe from Earth, from late October through early December 2025, was precisely the period when the Maven, MRO, and Perseverance data were most valuable. From Earth's perspective, 3I Atlas was behind the Sun and invisible. But from Mars, where the geometry placed the comet at a favorable angle, continuous monitoring was possible throughout this period. The Mars missions effectively served as a relay point for the global observing campaign, maintaining scientific contact with the comet during the weeks when Earth-based observatories were blind to it. What emerged from combining all of these observations was something unprecedented in the history of planetary science. For the first time, scientists had a 3-dimensional, multi-wavelength, time-resolved portrait of an interstellar object captured simultaneously from multiple platforms spread across hundreds of millions of miles of the solar system. Each observation contributed a different piece of the picture. HiRISE provided the highest resolution optical imaging of the coma structure and the X pattern jets. Maven provided the ultraviolet chemical characterization and water production rate measurement. Perseverance provided the surface-level historical marker. Punch provided the inner coma and tail morphology and polarized light. Lucy provided the perpendicular viewing geometry. Juice provided the post-perihelion structure as the comet retreated. And Webb, observing from Earth orbit, provided the infrared spectroscopic chemical fingerprint that the whole campaign would ultimately be remembered for, including the June 2026 Nature paper, revealing deuterium enrichment 30 times beyond anything in our solar system. The 0.18 astronomical unit closest approach to Mars on October 3rd, 2025, was the defining geometry of the entire campaign. That distance, roughly 2.7 million kilometers, was close enough that spacecraft in Mars orbit were positioned better than any other platform in the solar system for studying. 3I Atlas during the critical week around perihelion, when the comet was most active and most chemically productive. The closest MOID, the minimum orbit intersection distance, between 3I Atlas's trajectory and Mars orbit was calculated at precisely 0.08 astronomical units in pre-encounter computations. The actual closest approach on October 3rd matched that calculation with extraordinary precision, a testament to the accuracy of the orbital determination work that JPL's small bodies team had conducted in the weeks following the July 1st discovery. To put that distance in the most human terms possible, the Moon is roughly 0.06 astronomical units from Earth on average. The 0.018 AU closest approach of 3I Atlas to Mars is about 7 times the Earth-Moon distance. That sounds like a comfortable margin, and in terms of any collision risk, it absolutely was. But in astronomical terms, for an interstellar object arriving from outside the solar system at 130,000 miles per hour to pass within 7 Earth-Moon distances of a planet it had never encountered before, while instruments on that planet's surface and in orbit around it were watching and recording, is a convergence of circumstances so precisely calibrated by the geometry of the solar system that the planetary science community recognized it as a once-in-a-generation opportunity from the moment the orbital calculations were first completed in July 2025. No amount of mission planning could have deliberately placed 3 NASA spacecraft at Mars at the exact moment when the first confirmed hyperbolic interstellar comet in history made its closest planetary approach. The Perseverance rover had been on Mars since February 2021 for reasons that had nothing to do with interstellar comets. Maven had been in Mars orbit since September 2014, studying the planet's atmospheric evolution. MRO had been circling Mars since 2006. Their presence there in October 2025 was a consequence of the long-term investment in Mars exploration that the scientific community and NASA had made across decades, for reasons that had everything to do with understanding Mars and nothing to do with anticipating interstellar visitors. And yet, when the opportunity arrived, they were there, ready, capable, and precisely positioned to see something that nobody had ever planned to observe. The data from the Mars observation campaign continues to be analyzed and published as of mid-2026. Papers from the MRO, Maven, and Perseverance observation teams contributed to a body of literature that represents the most comprehensive scientific response to any interstellar visitor in history. The next interstellar object will not necessarily pass this close to any planet with instruments on or around it. The geometry that placed 3 operational NASA missions at Mars during the 3I Atlas flyby was a coincidence of extraordinary fortune that the scientific community exploited to the maximum extent possible given the compressed timeline available. What 3I Atlas passed by on October 3rd, 2025, at 0.018 astronomical units from a planet that may once have harbored life, was not just Mars. It passed by everything that humanity had ever managed to place in the Martian environment. 2 orbiters that had been circling that planet for years, performing the quiet, continuous work of monitoring a world we hope to one day visit. A rover digging samples from an ancient riverbed, looking for the same chemical signatures of water and organic chemistry that the interstellar comet was carrying frozen in its nucleus. All of them turning, for one extraordinary week in October 2025, to look at a visitor from another star that had been wandering the galaxy since before our solar system had a name, before our sun had ignited, before any atom of Earth had been assembled into anything resembling a world. And then 3I Atlas passed by, growing fainter and colder and more distant with each passing month. It will not return. But what it left behind in the data will last far longer than the week it spent as the most watched object in the solar system.